We're going to talk a bit about what goes into a definite integral. The Calculus 2 course, more than anything else, is really about integrals. So even though you were introduced to the concept of an integral toward the end of Calculus 1, it's important to start the course with a common understanding of what really goes into an integral, what the expression that you see, what the integral expression actually means. So let's go back to what you first learned about area in Calculus 1. If you think about it, when you're first introduced to the concept of finding the area under a curve on the interval AB, uh, the first exercise was to find the approximate area. So what we would do is we take the region, we take an interval AB and subdivide it into four segments. Usually it was four, it could be any number, but let's do it with four. So we'd say that we're going to have four segments and that each of the segments is going to have a width that we call delta x. Having done that, what we want to do is pick some arbitrary point. We usually pick the right endpoint of each segment and say that we're going to use that to form the height of the rectangle. So here, if you look at the pink rectangle, the first segment, its right endpoint has a value of x1. So what that means is that just over the number x1 on the curve, we get the point x1 comma f of x1. Since the y value is f of x1, which you see right there, that means that the height of the rectangle is f of x1. So I can write out an expression for the area of the pink rectangle, which is just going to be f of x1 times delta x1. So I'm sorry, times delta x. And what you'll see is that this is the height of the rectangle times its width. We can do this for all the rectangles. I wrote them out because I don't want you'd have to wait for me to write them all. But as you can see, I now have an expression for the areas of the blue, yellow, and green rectangles as well, and they all look basically the same. It's just going to be f of x for some value of x, that gives you the height of each rectangle, times delta x, which is its width. It's that expression involving a height times a width that becomes important in forming and understanding the definite integral. So here what we've done is we've written an expression not for the exact area under the curve, but for the approximation of the area under the curve. It's just going to be the sum of all four of those rectangles. So where does this bring us, and what does this have to do with integrals? What I want you to do is imagine that instead of having four rectangles, suppose that I had written infinitely many very thin rectangles instead of four. That's really what the integral is doing. If you can imagine that four rectangles is a decent approximation, so using 100 rectangles would probably give us an even better approximation. 1,000 would be even better. So if we use infinity rectangles, we'd have the exact area. That's really what the integral represents. So when we form an integral, what we do is we first of all, the width of each of these rectangles is going to be called dx. I know in Calculus 1 you probably covered the technical distinction between delta x and dx. I don't want to get into it. It's not necessary to understanding this point. Just assume that when we're talking about an integral, the width of the rectangle is dx. And similarly, we can also say that the height of each of these rectangles is going to be f of x for some value of x. Now, of course, what the a and b in the integral mean is that we're going to plug in all the possible values of x from a low point of a to a high point of b. So the point is that if you look at, this is the way that you want to look at an integral. The expression after the integral sign is really the area of what we're going to call a representative or typical rectangle that we're adding up. So In this case, what you can see is that, once again, we have a typical rectangle. The blue rectangle is just one representative or typical rectangle under the curve, and its width is dx and its height is f of x. So what that means is that we can say that the area is equal to the integral from a to b of f of x dx, where this, sorry, I want to put that in red, where this is the height of a typical rectangle and this is its width. So the expression that you see after the integral sign is actually the area of the rectangle, the area of a typical rectangle. And by the way, I want to emphasize here, do not forget the dx, because if you understand that what goes after the integral sign is supposed to be an area of a rectangle, the dx is important. If you omitted the dx, you'd only have the height of the rectangle, and what you want is its area. Now, I want to point out that if you look at the integral sign, it looks a little bit like a stylized S. This is not a coincidence. Uh, you can think of the S as being like a sum, as standing for sum, which in fact is why it looks that's why the symbol looks the way it does. The In a very real sense, what the integral is doing is it's finding the sum of the areas of all possible versions of the representative rectangle. In fact, just to make the point, I've shown here that if you start with the letter S and you start making it thinner and straighter, you actually do get to the integral sign. So it's important to think of the integral as a sum, that it's really the sum of all the representative rectangles. Oops. Now, um, you may be thinking to yourself, wait, what is this sum of representative rectangles? I know I learned what an integral was. I know it has something to do with antiderivatives. Didn't we sort of reverse the derivative process and then perform a subtraction problem? Wasn't that really what the integral was about? If you're thinking that, it's very likely that what you're thinking of is not the integral itself, but rather a theorem about integrals. It's a very important theorem. In fact, it has a name that's very grand, appropriate for its importance to the course. And that theorem I'm going to put up a figure for the next problem that you'll see. I'm just going to put up the figure for the next problem that you'll see. And as you do this problem, there should be an X in the upper left corner of the problem box. So if the problem box is blocking this figure, just click that to temporarily make the problem box go away so you can look at the figure. Okay, now I know that some of you are thinking, hey, I learned about integrals and this is not what it's about. What is this thing about sums of rectangles? I know that integrals were really about, they had something to do with antiderivatives. Isn't that what we did? We sort of reversed the derivative process and then did a subtraction problem. Wasn't that what integrals really were? Well, if you're thinking that, you're probably thinking not about integrals, but about a theorem that's a theorem that relates to integrals. This is a theorem that is very important and it has a very grand name that's befitting its importance to the course. And the name of that theorem is the fundamental theorem of calculus. And what that theorem says is if Now, some of you are probably thinking, wait a minute, I learned about integrals, and what integrals are about is finding an antiderivative. I remember this. There was something about sort of reversing the derivative process and then doing a subtraction problem. Wasn't that what integrals really meant? Well, if you're thinking that, you're probably thinking about a theorem that relates to integrals, not the integral itself. That theorem it has actually a very grand name to it, a name that's befitting its importance to a calculus course, and the name of that theorem is the fundamental theorem of calculus. So what the fundamental theorem of calculus says is that if we have a function capital F, which is an antiderivative of lowercase f, in other words, if the derivative of capital F is just the same function as lowercase f, then the integral from a to b of lowercase f dx is equal to capital F of b minus capital F of a. That's probably what you're thinking of. This is a way of finding the value of an integral. It's not really what the integral is defined as. This doesn't in any way help us set up an integral. It just tells us how to calculate one once we've actually set up the integral. So this is certainly an important theorem, and it's one that we're going to be making extensive use of in this course, but it's not what the definition of the integral is. Oh, and by the way, if you took Math 151 in the spring, you would have used our Rogowski textbook, which refers to the theorem I wrote here as the Fundamental Theorem of Calculus, Part 1. And if you've purchased the textbook that we're using this semester, which is Thomas's Calculus, it refers to this theorem as the Fundamental Theorem of Calculus, Part 2. I'm not going to quibble about whether it should be Part 1 or Part 2 of a theorem. This is actually the important part of the theorem that we're going to be making use of in this course. But the important thing to remember is that it is actually a theorem. It's not really the definition of the integral itself. One thing I just want to remind you of is that if we're using an integral to find an area, then since the integral is a sum of whatever appears after the integral sign, it makes sense that the thing that appears after the integral would be a little bit of area. It's not, it wouldn't be, you wouldn't be integrating, let's say, just the height. For example, all we put after an integral, if we just wrote, excuse me, I didn't mean to write that in yellow highlighter. If I just wrote integral of f of x, this is just a height, it's not an area. So you actually do need the dx width, because then you have a product of height and width, so you do get an area. So you do expect that if you're trying to find an area, that the thing after the integral sign should itself be a tiny little slice of area. It shouldn't be a speed, it shouldn't be a height, it shouldn't be a width or a time. You'd expect it to be an area. Okay, so let's summarize what we know. First of all, the integral from a to b of f of x dx means that we're adding up the areas of all of these rectangles, and we're doing it as the number of rectangles approaches infinity. So in other words, think of an integral as meaning add up an infinite number of rectangles whose area is given by the expression f of x dx. Next, the fundamental theorem of calculus says that we can evaluate that integral by finding an antiderivative called capital F and then calculating capital F of b minus capital F of a. This is a way of calculating an integral. It's not the definition of the integral itself. Third, and probably the most important point, is that when you're setting up an integral, in the expression integral from a to b of f of x dx, f of x is the height of a typical rectangle and dx is its width. So you should understand the expression after the integral sign in this way that I've highlighted here, where the expression after the integral sign is the area of a typical rectangle. And finally, remember that the integral sign looks a little bit like a letter S for sum, so you should think of it as adding up the areas of all the typical rectangles.